One for Lab 4. Okay. Lab 4 part 1 requires us to invent a stepper motor controller. The motor can turn clockwise or anti-clockwise. There is 3 input, which is EN, CW and clock. When the EN is 0, the output of the motor remains fixed. When the EN is 1, the output changes according to the timing diagram and direction controlled by DIR. The CW, when CW is 1, the motor will turn clockwise. When CW is 0, the motor will turn anti-clockwise, and it is clock input. So when it is turned clockwise, the output will be O0, O2, O1 and O3. If it is anti-clockwise, the output will be O3, O1, O2 and O0. This is our state diagram. The state diagram consists of 2 inputs, which is EN and CW. When the EN is 0 for the 8 cases here, it will loop into itself. When the EN is 1, CW is 0, it will turn anti-clockwise. But when the EN is 1, CW is 1, it will turn clockwise. This is our table. This is the output, and this is FF input. This is our K-map for JB, KB, JA and KA, and this is the 4 equation for JB, KB, JA and KA. This is the output equation function, and this is our schematic. We are using 74HC86, 74HC00, 74HC107 and 74HC08. And this is our input EN, CW and our clock input, and this is the 4 output, which is Q0, Q1, Q2 and Q3. This is our connection. So now I will demonstrate my circuits. The red input here will be our EN, the black input here will be our CW. The first 4 LED will be our output, and this is our stepper module. So now we will look at the output. When the EN is 0, whenever the CW is 0 or 1, the output does not change. But when the EN is 1, the output changes from Q0, Q3, come from 0, 0, 0, 3, 0, 2, and 0, 3. And if the CW is on, then it will be reversed, which is 03, 00, 02, 01. So now I will demonstrate my stepper module. So now when the EN is 0, whenever the CW is 0 or 1, the stepper does not move. But when the EN is 1, the stepper moves anti-clockwise. When the EN is 1, the stepper moves clockwise. Thank you. We are doing part 2 of Lab 4. We are required to design a linear feedback shift register. The second XOR gate can be used to invert the value at X3 by connect the ground input to VCC. When the counter is at initial state of 000, the second XOR gate can connect from ground to VCC to change it. This is the sequence that we obtain. This is the state diagram, which is 000 loop into itself, and another one is this state diagram. This is our schematic. 3 bits LFS error. This is 74HC164. This is 74HC86. This is our circuits. Okay. This is our second XOR ground input. This is our master reset. And this is 74HC164. This is 74HC86. When it is state of 000, it will loop into itself. And when I connect the ground input to VCC, it will start to operate. Okay, this is our circuits. So channel 1 is the clock signal, and channel 2 is our X0 signal. So this is our graph obtained. It is same as our prediction. Thank you. We are doing second part of part 2. This is our 7-bit linear feedback shift register. So we are changing only 2 wires, which is from X1 from pin 4 to pin 6 and X0 from pin 5 to pin 12. So this is our design, and this is our graph obtained. So I will demonstrate my graph. So you can see that we can obtain PDO random bit sequence. Thank you. We are doing part 3 of Lab 4. We are required to design a milli-step machine to detect the sequence of 011. This is our state diagram, this is our table, and this is our equation for DA, DB, and F. This is our schematic. This is 74HC74, 74HC00, 74HC08, 74HC08. As it is a milli-step machine, the output depends on the input. And this is, we are using D-type flip-flop. This is our circuits. The front parts here is from part 2 and the back parts is from part 3. And this is our graph. As you can see, there is normal operation of when found 011, 011, 011. There is some delays because of this milli machine here. Thank you.